In this example now, we show that the transform is indeed a special case of a critically sampled filter bank with the above computed filters. So let's take an example signal of length equals to 8. So here what we're doing, we are having here a signal length equals to 8. We have this array here, and then we do its decomposition into blocks of length 4 by using this convenient Python NumPy indexing here. So we have here decomposition into blocks of length 4. Again, we obtain our DFT transform matrix using the FFT and I, so we have here, and we obtain the transform blocks with this dot multiplication of our decomposition into blocks of length 4 and our transform matrix. And this is the result y of t. Here, each row contains the spectrum of each corresponding block. Now, we process the input signal x through a critically sampled filter bank with the equivalent filter impulse response. The transform matrix columns flipped up-down and down-sampled with the last phase of the blocks n0 equals to capital N minus 1, which is equal to 3, as it appeared in our derivation of the equivalent impulse responses. So here we have this filtering, so we are flipping, and here we get the output of this filtered signal through a critically sampled filter bank. Now let's compare with y of t. So y of t was given here, and now y is given here. And we see that y of t from the transform and y from the critically sampled filter bank are indeed the same. So we did two different procedures. Here we did a matrix multiplication, and here we did filtering. So using the critically sampled filter bank with the equivalent filter impulse response, but we achieved the same results. In conclusion, we see that a transform is a special case of a filter bank. The tool of reading out the impulse responses from a transform matrix allows us to analyze the resulting filters and to judge if they fulfill our requirements.